So, all right. So first, I would like to thank you for the invitation, for the chance to talk to you. So what I'm going to talk about is about general scattering theory, which works for both linear and nonlinear equations. And so the first work in this direction was done with Baoping Lu, who is a professor at Peking University. And most of the works that came later that I'm going to discuss is by, together with my former student, Xiaoxu, as you will see from the works, a brilliant student, not just a student. And very recently, we also did some work with my postdoc, Gavin Stewart, which did some extensions to one dimension, which is much more difficult than the three-dimensional case and higher. And even more recently, with another postdoc, Yorgos Mavrogiannis, we actually did similar things for the wave equation. So basically what I say about the Schrödinger also true for the wave equation. Okay, so let me start by telling you what is scattering theory, at least for me. We go back to Leonardo da Vinci. He said the air that is between bodies is full of intersections formed by the radiating images of these bodies. So it is well known that it's hard to understand what Leonardo da Vinci was writing. So here is what he actually meant to say, that these are the two meta-theorems of scattering theory. There are two. One is that if you have a physical system which depends on time, it is dynamical. If you wait long enough, it breaks into pieces, and each piece is moving independently, and then each one of them has its own dynamics, and it's very simple, right? You look at any system in life, you will see that this is always like that. You wait long enough, things becomes very simple. And the other part of the scattering theory, which is much harder to use, but maybe not to prove, is that once you are able to find all the scattering states, all the asymptotic states, but in the sense of asymptotic completeness, in other words, you have to find all of them, then you can reconstruct during this mapping, using this mapping, you can construct every property of the system. So in other words, you can tell everything about the system if you just find asymptotic states. It sounds great, right? I mean, you take a complicated person, you wait long enough, you look what happens, and then you say, okay, from this I can tell everything. But it's an open system, so it's not so easy. Okay, let's go. So what is it that we want to prove? So we want to prove that if you have a light wave interacting with the Mona Lisa, then what happens? At minus infinity, you have a state which is a free wave, electromagnetic wave, and plus the static picture, which is the Mona Lisa. As t goes to plus infinity, we have still a free wave, plus infinity, and the static Mona Lisa, but the free wave takes everything with it. The asymptotic set has all the information about the picture. Now, how to prove such a thing? How can you prove such a thing? I mean, Mona Lisa is a system of 10 to the 27 or 8 particles. All right, so let me just tell you a brief history of what was done in scattering theory. I will not have time to actually tell you the great thing that these people did, but many people here would recognize. So it was Sommerfeld who introduced the notion of radiation condition. This allowed basically to reduce scattering problems to solving elliptic problems instead of dispersive equation. So the time gone. So that was very important. Of course, there were other contributions in this direction at the same time. Now, all of this work up to this year were done, scattering theory was about electromagnetic waves. Now, in 1911, Rutherford came up with this great idea of using scattering theory in order to find the structure of an atom. So he actually developed the scattering of particles, charged particles on an atom. He solved the problem of Coulomb scattering. He did the experiment and he proved that the atom has a nuclei, and he also got a Nobel Prize for this. Okay, now what happened next? Until 1977, time-independent methods were the name of the game in scattering theory, and it culminated with the work of Fadeev, who solved the three-body problem. When I say asymptotic completeness, I mean find all possible asymptotic states and prove that they are what we expect them to be. In 1978, Volcker-Enz introduced a new approach, time-dependent and micro-local in some sense. Once again, it was another revolution from the point of view of at least mathematical scattering theory. And this leads to the modern works. So quantum mechanics is fundamental problem, even though at the two-body level, and even though it started in the 20s, people work on it until today. The three-body was done by Fadeev in '63. Enz did it in his method by much more general potentials and basically the optimal situation. And then there was another version by Moore and Segal, where the Moore theory that came after, inspired by the work of Enz, was used. So as far as the n-body problem is concerned, so this is a problem that I solved with Segal, and it required development of phase space analysis, which is adapted to multi-channel scattering, so it became much more complicated than the original work. We did not use the way Enz did things, but other methods. And it has some impact on the work that I'm going to talk about now. There was a simplification by Graf, and then many other works came later. In quantum field theory, there are also some preliminary results which also use micro-local analysis, but it is still not something that one can say, we solved the problem. Okay, now we come to nonlinear equations. Nonlinear equations, it's a much more difficult problem because I am focused only on the case where it is not completely integrable. So in the completely integrable case, people know what is asymptotic completeness. They know that every solution of, say, NLS has to be a soliton plus radiation, or many solitons plus radiation, something like that. Okay, but this is, of course, one particular soliton. So there are other equations for which there are all kinds of other interesting solutions, not just solitons, there are breathers and kinks and other things. Okay, so what to do if the system is general, not completely integrable? Then you have to do something else. And so the first works in these directions were to prove asymptotic stability, which is really to prove asymptotic completeness, but for an initial condition which is close to an exact solution of the nonlinear equation. These exact solutions which are close, these exact solutions of the nonlinear equations are not necessarily solitons. They are called coherent structures. So what is coherent structure? It could be soliton that we all know and love, but it could be breather, kink, vortex, black hole, hedgehog. There are many more strange names. All of them are considered to be coherent structures. So they are coherent structures in the sense, there is a reason for this name. It means that somehow the nonlinear wave coupled to the linear dispersion together in such a way that they form an object which has a location and structure. Okay, so you make a small perturbation and you want the solution to survive. Otherwise, it's not physically interesting. So, so the first works in this direction that for dispersive equations, it was the works of Michael Weinstein and me, and where we basically used, we introduced this possibility of, in the non-completely integrable case, you decompose the solution into soliton, for which you write a modulation equation. And in order to get a unique decomposition, you have to use orthogonality conditions. So this was basically the idea that was used in these works. And then Galina Perlman did the one-dimensional case. We did something simpler, 3-dimension with potential. Galina Perlman did the one-dimensional case with solitons. After that, there were many, many more works. I think you heard many references about it. I just want to mention some hot topics. So for the nonlinear Klein-Gordon equation, the object that is of interest is in fact king and not soliton. So more or less people started working on the stability problem in 2010, and the latest work that I'm aware of is by Luhrmann and Schlag and collaborators for the Now for the nonlinear wave equations, it's a different story. The main thing about asymptotic stability that I would like to point out is that if you put the system on a lattice, actually you can prove that the breathers are stable, unlike in the continuum. And therefore, there is a question of stability, and there were some results in this direction for the breathers. There are other coherent structures for people also worked. Of course, for general relativity, Minkowski space-time stability is another example of this, this result going back to Studulo and Kleiderman, and there are the very recent works on stability of Kerr black holes. Okay, so now let's talk about, so you see, up to now, everything was in terms of a small parameter. So now I want to talk about the case that there is no small parameter. It's a general theory. What can we do? So let me just give you, first of all, notation. The physical system, we assume it's given by a vector in the Hilbert space. And at the state at time t is given by an operator u acting on psi of 0, linear or non-linear, doesn't matter, right? And this operator is unitary because it preserves the L2 norm. So in other words, it is a system for which you can find conserved quantity out of which you can construct the Hilbert space. All right, so what can happen as t goes to infinity? Here are the possibilities. Well, first of all, it can blow up in a finite time. If it blows up in a finite time, we exclude this case, either by taking equations for which there is no blow up, or by taking only the solutions which survive for all times uniformly in H1, let's say. And if they do survive in H1 for all time, what can we say? Well, we can say that the free wave can come out by some free dynamics U0. We can say that solitons and other coherent structures come out as asymptotic states. We can say that there is something in between these two, which I call weakly localized wave, which are self-similar, but they are sub-ballistic. In other words, they spread, but not like a free wave. And if all of this is not true, then maybe there is a chaotic part to the solution as a function of time. So asymptotic completeness, really, for a real system, is to find all possibilities that come out for a given system. Okay, so what is known in this direction? So the main result, which is known in this direction, started with the work of Tao. In fact, a series of works between 2004 and 2014. He looked at the intercritical nonlinear Schrödinger equation in 3 or more dimensions and with spherically symmetric data and with solution uniformly bounded in H1. And he proved one of the key steps that you expect from scattering theory in general is that the solution at time t breaks into a free wave asymptotically plus a weakly localized part, and the convergence is in H1. And now we want to know more about the weakly localized part. So at least in one case, he could prove, one type of nonlinearity could prove that actually the weakly localized part is smooth. The initial condition is in H1, but the localized part is smooth. And moreover, the weakly localized part can be broken into localized part plus correction in order H1 dot. You see, the interesting thing here is that he proved that if there is a weakly localized solution, it cannot be just spreading all over. It must have a part which stays around forever. And this result is, as you will see later, is only true for intercritical equations. And this is actually the weak part of the story. It's not good to do asymptotic states in terms of H1 dot. Why? Because H1 dot, you can have part of the solution which is in L2 with mass 10 and H1 dot 0. So this means that you lose a big part of the solution at infinity if you just solve the problem in H1 dot. You can't do scattering theory for Schrodinger equation in H1 dot. It has to be done in L2. All right. So, sorry. So then there was, after that came a lot of works started with Koenig and Merrill. A lot of work that started by Koenig and Merrill, Descartes, Collot, and they actually looked at the critical nonlinear wave equation and 3 and higher dimensions in the spherically symmetric case. And in this case, they were able to get a complete understanding of the asymptotic states. So what does it mean, complete understanding? This is the critical equation. So for example, in 6 dimension, which is just came out, they proved that every solution which is every solution U of t either blows up in a self-similar way in a finite time, or it breaks into a free wave plus self-similar solutions. And the profile of all the self-similar solutions is the unique ground state of the elliptic equation. And here order H1 dot is okay, because L2 norm is not conserved for the wave equation. So this is a perfect result. What? Sorry? U squared. No, this is, sorry, it is, the equation becomes, maybe the number is wrong. It has to be U squared. Yeah, it has to be U squared. I don't know this number. Probably there is missing extra U here. I think extra power of U is missing. Extra power of U is missing. It has to be U squared in 6 dimensions. Okay, so now let me talk about the new results that we have. So first of all, let me talk about the case where the nonlinear, I shouldn't call it nonlinear. This is the interaction term. So the interaction term, let's look at the Schrodinger equation with, let's say, the free Laplacian for simplicity. And then you take the interaction term to be a general function of absolute value of psi x t. And you look at this equation, and you assume that the solution is in H1. And the condition on n is very general. I will explain in a moment. And so what do we want to do? We want to say that in this case, if the solution is in H1, and if this interaction term is localized in some sense in space, uniformly in time, this is the condition on the interaction term. It's localized in space uniformly in time, in some sense, right? Polynomial, that's what I mean. And if this term, n times psi, which is nonlinear, if this term is a nice function for each t, in the sense that the L2 norm of j times this quantity is in L1 in time, then you have the result. In other words, psi of t is given by a free wave plus a weakly localized part, and the convergence is in H1. In other words, under these conditions on the nonlinearity, no matter what is the nonlinearity, in fact, it is more general than I wrote, because n does not have to be a function. You can also put metric perturbation, which is localized in space-time. Then these conditions imply that the solution breaks into a free wave plus weakly localized part. If I didn't say anything about the weakly localized part, it only means that I can always prove for general system that the free wave goes out. So what's left for a general problem to do is to understand the localized part. Yes. Yes, of course, this is the most important thing. If you know how to choose JF, you solve the problem. What? Here? V is velocity. V is velocity. Okay, so let's continue. All right, so, okay, so next, here is some information that we can say about the weakly localized part. The weakly localized part is actually smooth in the sense that it belongs to HS for large values of S, depending on the smoothness of N. So for example, if it is purely nonlinear interaction and it is analytic in both psi and psi star, then it is possible to prove that it is infinitely smooth, because you can iterate the proof. You can iterate the proof that shows that the localized part is smooth infinitely many times. So, okay, and then the leftover is self-similar. All right. So, what is the result in 3 or more dimensions? This is in 1 dimension. In 1 dimension, in 1 and higher dimension, we need the localization. We need the assumption of localization of the interaction term. But in 3 or more dimensions, we don't need the assumption of localization. And because in 3 or more dimensions, we don't need the assumption of localization, it actually applies also to the non-spherically symmetric case. So again, if sup over time of n times psi is in some, let's say L1, so it has to be A to be sufficiently small, and the solution is uniformly bounded in H1, and then you can find the operator J, which is a projection operator. It's equal to 1, and I'll tell you in a moment where, and you will see that it's obvious. So then if this term decays fast enough in time, integrably in time, then we can prove that the free channel wave operator exists, and therefore the solution breaks into a free part plus localized part. Yes? What? No. F is an arbitrary function in LA. LA. A is 1, let's see. J, I said, this is localization operator. It is an operator which is equal to 1, and I'll explain in a moment how to choose it. All right, so how do you prove that the free channel, how do you prove that the free wave comes out of the system? You prove what is called channel wave operator exists. What is channel wave operator? So channel wave operator is something that physicists introduce in the study of n-body problem. You take the full solution at time t, you project on something which localizes the solution on the channel that you want, and then you go backward with the free flow. If it is the free flow, you can choose here U sub A for any channel you want. It doesn't have to be free flow. And you prove that the strong limit exists. It's crucial that you prove the strong limit exists. And if you prove that the strong limit exists, you constructed this operator. This operator is called Moller wave operator, and or the Moller scattering wave operator. And there are 2 of them. One goes for t plus infinity, the other goes to t2 minus infinity. This was introduced in the 1940s, as far as I remember, by Moller. So using Moller wave operator, in principle, you can know everything about the scattering, even though physicists these days, at least the young one, don't know anymore what is Moller wave operator, because they use the S matrix, which is a product of these 2, which is, in fact, can be used even to define the theory, as people do know. So, but the molar wave operators are basically equivalent to the scattering matrix. You can use it. So, okay. So, okay, this is a summary of what I said. And now let's go to some examples, which I have to go very fast. So I will start with examples which are linear, but new results, even though they are linear, and you will see why they also apply to the nonlinear cases. So the first example is you put here a general, more general dispersive equation, and you take a potential which is time dependent. So this is an open problem, linear open problem. Why it's open problem? Because the potential is time dependent. So what can we do in this case? So first of all, we get that all global solutions exist rather generally for this kind of equations because you just check the condition that I showed before. And moreover, in 5 or more dimensions, we could do one more thing. We could prove that the weakly linear part is in fact localized. There is no part which is spreading, it's just localized. And for V, which is decaying fast enough in X, and without conditions on the T dependence. And so there are other more general results of this type that I'll mention later. So this is another problem which is new. This is a generalization of what is known as the charge transfer Hamiltonian. A charge transfer Hamiltonian is a potential in which you have localized potential, but you have many of them, and each one of them moving with a constant speed, and they move in different directions so that they do not hit each other, or they are allowed to hit each other once maybe. But here, so asymptotic completeness for this case has long history. It goes back to the first one who proved it was Yajima, who used Faddeev's method, because this can be reduced to the three-body problem. So he used Faddeev method in order to prove asymptotic completeness for this problem. After that, there were other proofs. So it was, for example, the work of Graf that gave another proof. But all of these proofs do not allow V to be time dependent. So we actually gave a new proof which also allows the V to be time dependent. In other words, you can have n blobs moving around with constant speed away from each other. Then everything else around them, which is interacting with them, asymptotically, we know exactly what it will do. Part of it will become a free wave, and the rest will attach to these blobs and move with them forever. That's what happens. So we had to assume here five or more dimensions, and the localization of V is very simple, and there is no radial symmetry, of course. Okay, I have to skip these results. So now I will just say that the weakly localized part has the following property. So this is something that we proved in general, that the weakly localized part cannot spread faster than T to the 1/2 in general. And here, that's what happens. The weakly localized part is localized in a ball of size T to the 1/2 around each one of these centers. Okay, now another problem that we did is a three-body quasi-particle. So this is a usual three-body scattering, except that the body is not body, it is a quasi-particle. So a quasi-particle, there are two types of quasi-particles. Quasi-particles are basically particles in which the dispersion relation is not given by p squared, it's not minus Laplacian, but it is, for example, square root of p squared plus m squared. And the other types of quasi-particles are in fact not particles, they are just the group velocity of some wave, which is localized, right? So they are really derived objects. So in this case, you have free Hamiltonian, which is like that. P1, P2, P3 are the quasi-momentum of these particles. And the Hamiltonian is given by interaction between them. So, so this is very difficult case because you cannot prove the Moore estimate in general for this. I mean, people could not prove the Moore estimate. There were special cases for which the Moore estimate was proved. But. So then, okay, so then for this case, we were able to prove that at least for three particles, this system behave as expected. So in other words, clusters go out and move independently of each other. Okay, now we are coming to the linear problem, which is the most important. This problem is about a linear potential, which is time-dependent, which is decaying at infinity like 1 over x squared uniformly in time, short-range potential. Nevertheless, asymptotic completeness break. So how does it break? It breaks because so there are some conditions which I'm going to skip about the localization of the potential and regularity of the minus Laplacian plus v and so on. And this is in 5 dimensions or higher. So what happens in this case is that we proved that there are solutions to this equation which are partly localized and part which is a free wave, as expected. But then there is another part which spreads. And it spreads like t to the epsilon for any epsilon which is less than half. So in other words, part of the solution is in fact self-similar solution which spreads in space. This weakly localized part is not non-generic. It is in fact asymptotically stable. So you can add perturbations to the equation and it stays. So it is really something that you cannot ignore if you have a physical model of which contains this part of the equation. By the way, why 1 over x squared is important? Because 1 over x squared actually by scaling means mass critical equation. So this brings me to say that if you look at mass critical equations, you are going to necessarily find solutions which spread and which are it's not something that you can kill. Okay, so okay, I don't want to give you the details because basically the way you understand this is by showing that there is another channel of scattering in which the asymptotic behavior is the dilation group instead of the Schrödinger equation. And so basically you prove the kind of existence of wave operator for the dilation operator instead of giving you the asymptotic behavior. This is, so here you can see some of the details which I have to skip, but we added, it is possible to add nonlinear terms to this equation and which are higher order, and you can see that it doesn't affect the result. You can still get a solution with localized part, spreading part, and free wave. All right, so now let me talk about nonlinear equations. So you can understand from what I said so far that nonlinear equations are just as linear equations with a time-dependent potential. So the conditions will be the same. Of course, in order to verify conditions for nonlinear equation, you have to do more work. And that's why we assume that the solution is in H1. And that's why we assume that the solution is spherically symmetric in many cases. Because if the solution is in H1, uniformly in time, and spherically symmetric, then by radial Sobolev embedding, we know that the solution as a function is uniformly bounded by 1 over r to some power in 3 or more dimensions. And we use this to get the localization that we need in order to do the scattering. Right? So because of this argument, everything I said about the linear problem applies to this kind of nonlinear terms. And these nonlinear terms is not, there's nothing special about them. You know, you can take any function you want. It's just that these kind of things appear in real life. So this is known as the saturated nonlinearity. There's missing bar here. I remember putting it back, but it fell again. So these are known as saturated nonlinearities. In some sense, they are most interesting from a physical point of view because when you have a solution that has blow up, you can always modulate it by extra terms in order to saturate the equation in such a way that all solutions are bounded, and this makes the equation in some sense more physically interesting. So this is, in fact, in many cases, there is also extra V of x at the bottom here. And so the power of the nonlinearity, by the way, can be very small. Even though it is very small, if you know that the solution is in H1, maybe there is no solution, but if you know that the solution, there is a solution, it's in H1, then you can still prove that the free part goes away. Okay. So how these things work? This. So for the wave equation, we did something very similar. And something interesting came out that in 4 dimensions and higher, we could actually prove that the weakly localized part is always localized. So this, of course, excludes the critical equation, because we know that in the critical equation, the solution is spread. But in a saturated type of nonlinearity, and whenever you have the H1 norm uniformly bounded, then we prove that the weakly localized part is in fact localized. The proof that the solution is localized, it's rather difficult. It's more complicated than the proof that the solution has a free wave. It's much more complicated. Okay, as I said, metric perturbations don't matter. You can always add them because they still satisfy the conditions of convergence that you need. Now we are coming to the issue of how to prove it, because I didn't tell you how to construct J. So now I want to tell you how to construct J. So we want to prove that the free channel exists. So in order to prove that the free channel exists, we have to prove that the channel wave operator for the free channel wave operator exists. So we have to choose J free. Now look at this equation. Look at this equation. What should be J free? J free should be a projection operator which is equal to 1 in the region of phase space where the free wave lives. We just heard in the previous talk a similar argument. You put J to be an operator which localizes the whole solution in the region of phase space. In fact, we use the extended phase space, include time. So in the region of phase space where the free wave lives. Now, this set in the phase space is very thin. Why it is very thin? Because all solutions of dispersive equations are quote-quote self-similar. For example, the free equation. The free equation, the solution is asymptotically a function of x over t. And all the self-similar solutions are functions of x over t to some power. So it's always self-similar. The localized part, it's x over t to the 0. So it looks like the set on which a solution of these equations exists is in fact very thin. Since it is very thin, if I put a projection on this very thin set, of course I can prove that the limit exists. It's much easier. So how to do it? That's actually, in some sense, a high school exercise. You see, x is equal to x0 plus vt, and therefore x minus v of k bounded by t to the alpha is where we want to project. V of k is the velocity operator. It is the group velocity of the wave, whatever the wave is. And in the special case of omega is equal to k squared, you just get 2k, and v of p is just minus 2i gradient, because that's the velocity operator. And so in short-range scattering, you can choose alpha to be very small. There's no problem, because a quantum wave or wave in general cannot be sharply sitting on x equal to vt plus constant. There's always a spread. In fact, you can see in some papers of Freeman Tataru, where they actually realized that in the long-range scattering case, there is a measurable spread of the solution around x minus vt. Something similar we saw Hans and I, Lindblad, in one of our papers, that the solution, even though it behaves asymptotically as expected, like decay in L infinity like t to the 1/2, it's still spread around the free flow a lot. So you cannot choose any alpha you want, but in the short range case, you can. And so far, we only did short range cases. So we could choose any alpha small that we wanted. Okay, so how to prove, how to construct the operator that we want? We just take a smooth characteristic function of the interval from 0 to t to the alpha, and replace the variable by the operator, which is absolute value of x minus vt. This is not a pseudo-differential operator. It's not. But it is micro-localizing in the phase space nevertheless, and we have to use to adapt the calculus to work with this kind of an operator. And in fact, many other operators that we use are also not, they are not pseudo-differential, they are more general, what I call phase space operator. Okay, so let's do the calculation. When you do Cook's method to prove that the free channel wave operator exists, then the term that you get by taking the derivatives, which has a nonlinearity in it, is, you see, you get two terms. One term is the derivative of the projection, and the other is the derivative that comes from the full dynamics, and you get the interaction term in. But when you look at it, you see immediately that you can use these identities, and you can move. You see, any function of x minus 2 pt, if you move e to the minus I Laplacian through this function, it kills the minus 2 pt, and you get function like that. Therefore, we move a factor of e to the IS0t, and we get this expression. And now you see that this times this times this times this times this has to be in L1 in time when you take the L2 norm, which implies convergence. That's where it comes from. What to do about the other term? What to do about the F prime term? The F prime term, you have to control with respect to the full flow. How can you control something with respect to the full flow? Well, there is a miracle here. The derivative of f prime is of order 1 over t. That's not integrable. However, it is also positive. Why it's positive? If you think about it geometrically, you will see that it has to be positive because it increases the volume on which it is projecting. So because it is positive, you can use this in order to get an a priori estimate, a propagation estimate, which implies integrability with respect to the full flow. And so this gives you the proof for the free channel. Okay, so it is possible to write the condition for the free flow in an abstract way. And the abstract way is the following. You take the projection on x over t to the alpha less than 1 for alpha sufficiently small. You project with another function the quasi-momentum p away from all the thresholds of your free flow, including infinity and 0. Including infinity and 0, you throw, so tau j are all the bad points in the thresholds here are in the sense that the derivative of the dispersion relation is 0. That's the definition. Okay? So you throw these points, you throw away the high frequency, and then all you have to do is to prove that this decays faster than 1 over t. And for this, all you need to know, for example, that n times psi is in L1, and that U0 has dispersion relation like free wave. That's why it works in 3 or more dimensions, because in 2 dimensions and 1 dimension, the dispersion in L infinity is just t to the minus half or t to the minus 1. You need more than t to the minus 1. So for this, you have to go to 3 dimensions. So here you see we are using dispersion, but not always. Sometimes we can use the fact that this is localized, that n is localized in space. Then we can get much better decay by localizing the frequency away from thresholds and using local-decay estimates, which gives faster decay in time. Okay. Let me skip all this. This is just the details of the calculation. Let me skip all these things because we need for this another 2 hours. But I just want to say that in order to prove local decay starting from this kind of estimates, you have also to do a lot of the compositions with respect to incoming and outgoing waves. And there are different ways of doing the composition with respect to incoming and outgoing waves. Here we use what I call analytic operators to do the decomposition. So it is basically analytic functions of the dilation operator. So the calculus is again different. And what I will save you from the painful part of how to prove local decay out of these things. And I will also skip the issue of what is a soliton and what is a soliton resolution. And I want to go directly to the open problems because I think this is the most interesting thing and it is related to that. So there are 3 problems that I think one should concentrate on. I mean, these are really great problems. I tell you why. I cannot tell you in detail, but so this one is breather in higher dimensions to prove or disprove that there is such a thing. And then there is quantum ping pong, and then there is inverse scattering. What is breather in high dimension? Breather in high dimension is, you see, we proved that the solution is localized and free wave. How to prove that the localized part is time independent? So if you can prove that every localized part has to be also time independent, you prove that there are no breathers in higher dimension. This is something that everyone believes in. It doesn't mean it's true. If you can find an equation, even artificial, for which there is a breather in higher dimension, you will be very famous, and all the physicists will hug you, because this means most likely is that there is a completely integrable system in higher dimension, and nobody knows how to do such a thing. So you see, this is a big problem which is hiding in this asymptotic completeness problem. And this is something which is much simpler, which has a lot of applications from all the problems that I'm trying to solve and I cannot, but it also has a physical meaning which is very important. Is it possible to find a way to localize a solution in L2? So how can you get a localized solution, time dependent or whatever, using a positive potential, which is time dependent, which is bounded, which is weakly localized, let's say it cannot spread too much, and it has to be relatively smooth in X space, and it can be pretty rough in the derivative with respect to time. So this is the question. And because it is positive, it has to be time dependent, because if it is positive and time independent, there is a proof that there are no bound states. But if it is time dependent, can you play ping pong? Can you kick a particle, quantum particle, can you kick it this way so that it will stay more or less here with the tail at infinity? It's very important, actually, to certain quantum devices to be able to do such a thing. The last thing that I want to mention is that inverse scattering is completely open. Very recently, there have been very beautiful results on the problem of inverse scattering, which actually answer the question in the nonlinear case by Philip, Vizan, Murphy, mostly, as far as I can tell. And the remarkable result is that it is sufficient to use small data in order to find the interaction term. In other words, it is sufficient to do scattering with small data to find the interaction term. But the question is how to find more details of the interaction. For example, how to find resonances if I give you the scattering matrix. Suppose I give you the scattering matrix for nonlinear equation, how to find the resonances. Physicists know how to do it in the time-independent case. They have no clue how to do it in the time-dependent case or in the nonlinear case. Right, let me leave you with this. Thank you. That's the end, I think. Yes.